So welcome all. So this is the continuation of the one-way slab part 2. Okay. So part 1 we have seen the concept, how to what are the steps that to be followed for designing a one-way slab. So in this video we will see a numerical and we will clear all our doubts. Okay. So let's start. So see the given, first we have a numerical, that is the given thing we will check once. Okay, so this is the numerical. Yeah, design a simply supported beam, design a simply supported slab of 3 meter into 7 meter. Okay, supported on all sides with 230 mm thick wall. It carries a superimposed load of 4 kilonewton per meter square with floor finish. Use M25 and Fe415 and use a cover of 25 mm. Okay. So if we write the given, so longer span of the slab is 7 meter. So Ly is equal to 7 meter. Shorter span is 3 meter. So Lx is equal to 3 meter. Okay. So the width of the wall is 230 mm. So we know that we have defined the width of the wall with b. So the both are the same. So we are taking it as b. So b is 230 mm. If you take superimposed load, means live load is given as 4 kilonewton per meter square. Okay. So FCK is 25 Newton per mm square and Fy is equal to 415 Newton per mm square. Okay, and cover is given as 25 mm. Okay, so these are the given thing. So you can see that I have drawn a diagram also. So this is the slab, mainly this is the slab. So Lx is equal to 7 and Ly is equal to 7 and Lx is equal to 3, and the support width is 230. Okay, so this is the top view of the slab. If we see the front view of the slab, so front view will be, see here, this is the slab. The clear span is 3. Okay, 3 meter. The clear span, we can also write this 3 meter as this clear span. Okay, clear span, the clear span is 3 meter and the width of the this support are 230, and this one is the slab. Okay, so mainly it is a simply supported slab. Okay, so we are starting the numerical. See, so what the first step, we can see it, it's mainly a one-way slab, we can see it only, but we will once check it. So step 1, so step 1, so step 1 will be type of slab. We will check the which type of slab it is. Okay, type of slab, Ly by Lx is equal to 7. The greater side is 7, the smaller side is 3. So if you divide 7 by 3, see here the value is coming greater than 2 only. Okay, 2.3 something like that. So hence it is a one-way slab. So it is a one-way slab. Okay, so the first part is done. So we will go to the next step. Okay, the next step is we have to assume a depth. Okay, so let's see how we will assume a depth. Okay, the step 2, assume depth. The depth of the slab. Okay, this is the depth of the slab we have to assume. So we know that there is a formula is L by D, means span divided by, we can say, small d. So effective depth is equal to a value. See, span is 3 meter. So if we write it in okay, so it will be 3000 divided by small d. See the a value for the cantilever, sorry, a value for simply supported beam is 20 up to a span of 10 meter. So here it is 3 meter only, the shorter span. So we can take the value. See here, yeah, a value up to 10 meter, the a value is 20. Okay, this one we are taking. Yeah. So yeah, so the a value is equal to 20. So from here we will find out the d. So it's coming to 150. D is equal to 150 mm. Okay. Yeah. Now we can calculate the capital D, as because the cover is given. Cover is given as in the numerical only as 25 mm. Okay, so the capital D will be small d plus cover. So it is 150 plus 25 is equal to, it is coming to 175 mm. So for the ease of the calculation, we are not taking it as 175, we are taking the capital D as 190 mm. Okay, so as we have changed the capital D, so the small d again will be 190 minus the cover, so it will be 165. That we have calculated 150, but in our further calculation we will take the value of d. We will take the effective depth is equal to 165 mm. Okay, see, now the next step will be calculation of the effective span. Okay, effective depth has been calculated, the depth. So the step 3 will be effective span calculation. Step 3, effective span calculation. Effective span, that is L effective calculation. Okay, yeah. So this is a simply supported slab. So for simply supported slab, we know that L effective is clear span plus D, or clear span plus half of the width plus half of the width, whichever is minimum. Okay, so we will do both the things. Is equal to clear span is 3000 plus effective depth we got 165, or another thing is 3000 plus 230 half plus 230 half. Okay, the width, half of the width. So in this case we are getting 3165, and in this case we are getting 3230 mm. So minimum we have to take. Yeah, so the value of L effective comes to 3.165 meter. Okay, the next step will be of the load calculation. Okay, the next step will be load calculation. So step 4 will be load calculation. Let's see. So the live load is given in the numerical as 4 kilonewton per meter square. Okay, it's given. So we have to now calculate the self weight. The self weight of the slab. Okay, so we will calculate. For this formula we know B into D into gamma unit weight into 1. Okay. So B, we have told that for slab design we assume B as 1 meter. Okay, so 1 into depth is, we have gone capital D as 190. See here, capital D as 190. So we will take it as 0.19 into unit weight of concrete is 25 into 1. So it comes to 4.75 kilonewton per meter square. Okay, one is this and one is this, and now we have to calculate. We have calculated live load, we have calculated this as dead load, and now we have to calculate floor finish. Okay, floor finish is equal to, we assume it at 1 kilonewton per meter square. So now we will calculate the total load. Total factored load. Total factored load as 1.5 into 1 plus 4 plus 4.75. 1 is the floor finish. Okay, 4 is the live load and 4.75 is the dead load. Okay, and 1.5 is the factor value. So if you do this, the value will be coming to 14.625 kilonewton per meter square. Okay. Now see the load we have got. So now we have to calculate the bending moment. Okay, so let's see how we will calculate the bending moment. So this will be the step 5. So step 5 is max bending moment. Okay, the shear force we can calculate also. So let's calculate. Okay, max shear force also. Okay, so see, bending moment maximum is equal to WL effective, WL square by 8. So WU is coming to 14.625 into the L effective. See the L effective as 3.165 3.165 square of this divided by 8. Okay, if you calculate it, the bending moment will come to 18.31 kilonewton meter. Okay, now we have to calculate the shear force max. Okay, so the formula is WL by 2. WL by 2. Okay, so it is coming to 14.625 into 3.165 divided by 2. Okay, let's calculate it. 14.625 into 3. The value is coming to 23.14. Okay, 23.14. Now we will calculate for this moment. Okay, now we will calculate for this moment. So step 6 will be check for moment. Okay, check for moment. Mainly in this check we will get the d value. The d assumed we have taken. So if you write it here, small d assume, we have taken it as, just erase it. Okay, small d provided. Okay, we have what we have provided. We have provided 165 mm. Let's see what we get it from here. Okay, so moment ultimate formula is qbd square. So here q for Fe415 is 0.138 fck. So here d will be mu divided by q into b. Okay, small b or capital B, it doesn't matter, the thing is the same. So moment comes to 18.31. okay, 18.31. We have to convert it into Newton per Newton per meter. So we will do 18.31 into 10 to the power 6. C 10 to the power 3 for kilonewton to Newton, and 10 to the power again 3 for meter to mm. Okay, so divided by 0.138 fck is 25 into b value is 1000. As we know, we design for b is equal to 1 meter in slab. Okay, so by this value we are getting d is equal to 73 mm. Okay, so this is d required. So you can say that d provided is greater than d required, hence okay. Yeah, now we have to do the next step. Let's see the next step is we have checked for the depth. Okay, now we will calculate the area. So step 7 will be main reinforcement. Okay, so the formula for area, it is the universal formula. So the formula is 0.5 fck divided by fy bracket 1 minus root over 1 minus 4.6 mu divided by fck bd square into b into d. You can write small b, capital B, whatever you want. Okay, just put the values. fck is 25, fy is 415 bracket 1 minus root over 1 minus 4.6 mu is 18.31 into, let's check one, 18.31. Here we have to again convert it into meter Newton mm. Okay, so 10 to the power 6. Again fck is 25 B is 1000, okay, and D is 165 square. B is 1000 into 165. Let's see. So if you calculate this, the value will come to 317.65 mm square. 317.65 mm square. Okay. Now, as per IS provision, we have to check for the minimum reinforcement. So we know that AST minimum for main bar is 0.12 for mainly for HYSD section. For mild steel is 0.15. Okay, so for mild steel it is 0.15, and for HYSD bar it is 0.12% of the section, cross section. So here it is HYSD 415, it is HYSD bar. So for HYSD, AST minimum is equal to 0.12% of cross section area. Okay, cross section area. So 0.12 divided by 100, B into D. Okay, so B into capital D. Cross section area is B into capital D. Okay, so the B is here, B is 1000 and capital D is 190. Okay, previously we have got it. So AST minimum AST minimum, it is AST minimum is 228 mm square. Okay, this is the AST minimum. See what AST we have got 317, hence okay. So you can write it here, hence AST main bar is greater than AST minimum. Okay. Now we have to calculate the spacing. Now we will calculate spacing. So before calculation of spacing, we have to just assume a dia of the bar. So let's say we are providing 20 mm dia for the main reinforcement. So say provide 20 mm dia as main bar. Okay, so let's see. So the spacing will be S is equal to, we know 1000 by number of bar. So number of bar calculation how will be done? AST into pi by 4 phi square. So here AST is 317.65 and pi by 4 into phi square is 20 square. So the spacing will come to 988.50 mm. Okay, so it's a huge spacing. Okay, so now what we have to do, we have to check for the minimum spacing. Okay, maximum, sorry. So we have to check for the maximum spacing as per IS 456. So max spacing for main reinforcement. Okay, so we know that for main reinforcement the maximum spacing cannot be greater than 3D or 300 mm, whichever of this is minimum. Okay, so if we find out this value, 3 into small d is 165 and here is 300 mm, so it is coming to 495 mm. So this one is the minimum of these two. Okay, so spacing will be provided as 300 mm center to center, hence spacing provided is 300 center to center. Okay, so hence the main bar thing is completed. Now we will go to the distribution bar. Okay, so distribution bar step 9, distribution bar. Okay, so mainly in distribution bar we don't have to calculate the distribution reinforcement. We don't have to calculate the area of the steel. We have to just calculate the spacing. Okay, yeah, one thing you can check also. See, the minimum has criteria, area of steel has been checked, so nothing is to be done. You have to just find out the spacing. Okay, so S is equal to assume as we have told, we will just downgrade one grade of dia. The main bar we have taken 20, so we can take it as 16 or 10. So we are assuming as 10 dia. Assume dia is equal to 10 okay. So now we will calculate the spacing. So 1000 divided by, okay, one thing we can provide. See, the area of steel, here it is coming as 317. So for the distribution bar we can provide this minimum value. Okay, so for the distribution steel we can, yeah, so this AST can be can be provided for distribution reinforcement. Distribution reinforcement. Okay, as that area of steel will be a huge value. Okay, 317. So we can provide the minimum value only in the distribution steel. Okay, so 1000 divided by 228 228 into pi by 4 into 10 square. Okay, so the spacing is coming to 345 Okay, so now we have to once check also. We have to check also the maximum spacing, max spacing for distribution bar, for distribution bar. Okay, so for maximum spacing for distribution bar is 5D. It should not be greater than 5D or 300 So if we calculate 5D, 5 into 165, it is coming to 825 or 300 So here also the spacing will be provided as 300 Okay, so hence provide spacing as 300 Okay. Now we will check for the deflection. Okay, so check for the deflection. Step 10, check for deflection. Okay, so if we check for the deflection, so L by D actual should be less than L by D permissible, okay, or equal to permissible. So see, L by D L by D actual, what is the value coming? So L by D actual is, see, L clear span we know L is 3000 and D we know 165, so the value is coming to 18.8. And LD permissible for a simply supported slab, it is 20. LD permissible for simply supported slab up to 10 meters span, it is equal to 20. So hence the slab is safe in deflection. Okay, so one thing we can check that we have previously missed, that is for shear. Okay, so now we will check for the shear. See here, step 11. Check for shear. Check for shear stress. Okay, so we know that we have to check that tau c should be greater than tau vu. Okay, nominal shear stress. So the section will be safe. So first we will calculate tau vu is equal to vu divided by b into d. Okay, so previously we know that we have calculated the vu value. See here, vu, wait, yeah, so it is 23.14. okay, 23.14, just put it here, 23.14 divided by b into d. Okay, so b is 1000 and d is 165. So this value will be coming to tau vu will be coming to 0.15 Newton per mm square. Okay, yeah, so now we will calculate the value of tc. Okay, so the tc will be a little bit long. Let's see, tc. So the design shear stress, it depends on percentage of steel and grade of concrete. Okay, grade of concrete. So we have to calculate first the percentage of steel. So percentage pt is equal to 100 into ast divided by bt. One thing here you can take it, see, if nothing is given as percentage ast, for our ease of a calculation in slab we can assume it as 0.25. okay, we can assume it as 0.25. see, so now grade of concrete is M25. From table 19, what we get? We get for 0.25 the tau c value is 0.36. okay, so see here, see, tau vu value we have got it as 0.15 Newton per mm square and tau c value is 0.36 Newton per mm square. So we can clearly see that tau c is greater than tau vu. So slab is safe in shear. Okay. Now we can do the detailing. Okay, just 1 minute left, so we will do the detailing also. So step 12. So step 12 is detailing of reinforcement. Okay. Okay, so first we will draw a slab from the mainly the side view. So this is the support. Another support we will draw it from here. Yeah, it's same. Yeah, now we will draw the bottom reinforcement first. Yeah, now freehand only we are drawing. Now we can draw the crank bars. Okay. Yeah, so this black one is our main reinforcement, and now we are drawing our distribution reinforcement. Okay, so our distribution reinforcement are like this. The Okay, yeah, so provide 10 mm dia bar. This is the distribution reinforcement at the rate spacing 300 mm center to center. Okay, now for the main reinforcement, provide 20 mm dia bar as main reinforcement at the rate 300 mm center to center spacing. Okay, and the given things you can write it here also, that is this width is 230 mm and this clear span is 3 meter. Okay, so we are ending up the lecture here. So our next will be of two-way slab. First we will see the concept and we will then see the numericals. Thank you.